Yeah, hi, I'm Adam Peterson. I'm your first speaker for the night. Currently a PhD candidate at the University of Michigan, pursuing my PhD in biostatistics. I'm working under Brisa Sanchez, who transitioned in the course of my PhD. She was at Michigan and now she's at Drexel, which is how I came to be in Philadelphia and learned about the DataPhilly group. And without any further ado, I take it I can go ahead and start my talk. There's no other administrative stuff to get through?
No,
I know it's all yours now.
Yep.
Okay, great. All right, so like I said, thank you to the DataPhilly organization here for giving me the opportunity to speak about some of my work. This work in particular today has been kind of a product of collaboration between myself and Brisa Sanchez, like I mentioned, who's my advisor at Drexel, but also Veronica Berrocal at the University of California, Irvine. And in kind of thinking about what this talk offers to you guys, I'm trying to get a very high level approach while still grounding things in examples so you can kind of see how this method might be motivated. But I've got some statistics to talk through. I've got some concrete application to talk through, and I've got an R package. So I'm hoping that no matter where you are in your kind of data analysis life, you can find something here to learn from. To speak more specifically about the motivation for why I'm working on this and why my PhD advisor is interested in pursuing some of this research, it comes from trying to understand the built environment. And for those of you who may have not heard that term before, I myself hadn't heard it before starting my research. It's kind of a catch-all term for anything that you might find in the area around where you live, anything that's been in some way touched or constructed by humans. So I have up here, stores, schools, parks. You could also think of tree cover. You could think of the amount of asphalt in your immediate area. Like there are a bunch of cars around. The overarching questions are how do those things affect us, and how does where you live in certain kind of spaces in the built environment either maybe protect or put at risk your health. In the kind of talk I'm going to talk about today, we're interested in features of the built environment that we can really kind of discretely pinpoint or model as a point pattern process. And that's why I have this picture here of elementary schools and fast food restaurants in California during academic year 2010. So we're going to think about the kinds of distances between these different points. So for example, between a school and a fast food restaurant, we're thinking of those distances as being kind of important for describing the kind of environment you live in, right? Because if you're near a bunch of, if it's very not too far to get to these kinds of amenities, then that's a different kind of exposure than if it were to be really far away. So the first question we're asking is, can we find these kinds of patterns in accessibility or exposure? The second question is, are these patterns relevant to our health? I'm going to spend the majority of this talk talking about or kind of exploring and constructing a method to answer the first question. And I'm just going to have a few slides, a little bit of notation, and then one slide of results to talk about the second question. So I can't really do this justice here, but I can definitely refer anyone who's interested in learning more to appropriate sources. So to basically maybe take things at a little bit of a higher level, make things a little bit more hypothetical and easier to understand than all of those points I had on this previous slide. Let's consider two hypothetical schools, right? I had schools on the other example. We're going to think about whether or not being near fast food restaurants when you're at a certain school if there's patterns in that kind of exposure and whether those patterns are meaningful. So on the left-hand part of the screen here, you can see that I have a school with a lot of fast food restaurants nearby. And on the right-hand side of the screen, I've got a school with fast food restaurants that aren't super close by. And there might even be a different number here. So it's kind of an abstract hypothetical. If we were to go from that to maybe doing some exploratory data analysis, one thing you might do is construct an empirical cumulative distribution function, right? So we want to see every time we go across some unit of distance, how often do we find fast food restaurants? In this kind of summary form, we can see that there's a major difference between these two kinds of schools. This school number one has a bunch of fast food restaurants close by. Another school has, maybe not quite the same number of fast food restaurants, but fairly close, but they're all further away. And this is important to think about because what a lot of people do if you were interested in asking these kinds of questions, what people typically do is they will just say, pick some radial buffer, like let's just look at all the stores within a mile of a school, let's count how many there are, and then let's just plug that into a linear regression and see if there's some effect. And the idea that we're kind of finding here, or something that I'm trying to suggest with these kinds of figures, is maybe we're missing something meaningful with that kind of ad hoc plug and chug approach, right? We're not capturing spatial proximity with these kinds of, as you can see illustrated in these kinds of curves. And we might potentially be missing something in terms of differences in quantity combined with spatial profiles. Moving a little bit further along this kind of hypothetical tract, what we would think might be a generative model, or the kind of underlying pattern describing those kinds of cumulative distribution functions I showed you earlier, were functions like these. So these are intensity functions. For those of you who are familiar with inhomogeneous Poisson processes, that's exactly what these are. For those of you who are not familiar with inhomogeneous Poisson processes, it's not important to know all the properties and the facts. All you need to know is that this line kind of describes how frequent the instantaneous rate, you might say, of a fast food restaurant occurring in some small, little interval of space. Or to put it in even maybe simpler words, for this first school, we see that close by it's very likely that there are a lot of fast food restaurants within a short distance from the school. And for school two, it's not very likely to find that many fast food restaurants close to the school. But then the pattern obviously changes as you go further along in distance from the school. Okay, so this suggests a new kind of question, right? We're kind of building up to something interesting here, which is, if we've got this kind of picture, this idealized picture of how we might find fast food restaurants, parks, or anything else around schools or where we live, and we're interested in kind of identifying these patterns, we need to kind of get some data on where schools are located to these kinds of amenities, and we need to estimate these densities, basically. These intensity functions can be thought of as kind of densities, so we need to estimate them. Well, how do we go about doing that? That's a little bit hard. And so the first thing that you might think of as, again, an out of the box, I don't want to reinvent the wheel here, what can I do? You might just say, oh, maybe I'll assume it's normally distributed, it's a normal density, right? It doesn't really look normal, but maybe you could just assume that. Well, again, the whole idea here is that would miss something really meaningful, because these functions, as I've kind of described here, and hopefully you can imagine in real life, they don't follow a very simple, easy to write out mathematical formula. So we need to allow for some flexibility in how these are estimated. The next thing you might need to think of is, how many kinds of intensity functions are there, right? Here I've just shown two kinds of idealized patterns for what schools might be like, or what fast food restaurants near schools might be like. But in reality, we don't know what kinds of intensity functions we might find. We don't know how many there might be, right? We would like to estimate as many of them as we have data to support. And that means we need, again, some flexibility in estimating these. I have here that there could be as many intensity functions as there are schools, but it's probably not the case that we have enough data to support that kind of question. We probably want to come up with some smaller number of intensity functions, or clusters, that we do have enough data to identify and then kind of link to a health outcome. So that's going to be our two questions that we want to overcome here. And I'm going to, again, kind of lead us down the pathway that maybe one thing we can do, one solution to this problem is to use a Dirichlet process. And what that would effectively do is allow us to express this observed density that we see. So if we were to combine those two densities earlier, right, you don't get to see these in real life. What you really see is all of the distances connected to schools across space. So you see something like this. If you were just estimating this global density and you wanted to estimate it flexibly, again, not using just one simple parametric form, you could use some smaller number of densities to do so. You could use a finite mixture model. And that would say, hey, we think maybe we could represent this density with just 4 normals and take a linear sum of those 4 normal densities at any distance, and that will be our density. Again, the obstacle you have to overcome in defending that method to someone else is, how do you know that 4 densities is the right number, the right quote unquote number of densities to use? And that's tricky. Typically, you'd have to do some kind of model selection or something a little bit arduous. So what's a very cool solution in Bayesian non-parametrics that's been developed is this distribution on distributions, basically a Dirichlet process. And I have one realization of what a Dirichlet process looks like on this slide. Here I'm just saying, oh, just pick a parameter mu, and here is one realization from a Dirichlet process on this parameter mu. So you can see we've got, it's a discrete mass function, a probability mass function. And what we could effectively use this Dirichlet process for is we could say, hey, we're going to use the linear sum of some finite number of, or some infinite number with the Dirichlet process, number of parametric densities, and we're going to weight them by the weights we derive in the Dirichlet process, and through the parameters we estimate through the Dirichlet process. Again, if this sounds kind of abstract, don't worry about it. I'm gonna have some pictures that illustrate what I mean on this shortly, but just bear with me for now and go with me. So if we did that, if we used this combination, this weighted linear combination of simpler densities, what we could do is we could estimate the global intensity function, like I said. So this big kind of weird, crazy thing, we could say, oh, this is actually just 4 smaller functions. We could estimate each of these as 4 smaller, simpler functions. And there's some weight by which we want to combine these all to come up with this. And that would be a solution to estimate the global intensity function of all schools, of the exposure from all schools to fast food restaurants. Now, again, that's not what we wanted. What we wanted was these kind of sub-densities. We wanted to say, hey, here's our global density. Let's split that up into some smaller density that might also still look weird, and have some parameters that correspond to those describing the probability that a school would belong to that sub-density. So in order to accomplish that, we need something a little bit fancier than the Dirichlet process. We need the Nested Dirichlet process. And this is where the foghorns from Inception should come in and kind of herald this quote, because to describe the Nested Dirichlet process, it's a little bit meta. The quote here from the original Rodriguez paper is, just as the Dirichlet process is a distribution on distributions, the nested Dirichlet process can be characterized as a distribution on the space of distributions on distributions. So that's a little bit, you know, I can't say that without smiling and totally agreeing that that sounds a little bit crazy and meta. But I have a picture here that, again, I'm hoping helps, so that you can see that we've got these G sub j. You can think of these as cluster-specific distributions, where we've got weights and parameters, but now we've got weights and parameters that are specific for one school. So school 1, or for some number of schools, they'll be assigned to the G sub j1 here. And some other number of schools will be assigned to G sub j2, that each have their own kinds of mixed non-parametric density estimates. Again, this might seem a little bit crazy, just hang on and bear with me here. Here's a picture of what this looks like matching the data structure to our intensity functions. So what your data structure looks like is some number of schools, right? Here's an index, 1, 2 through capital J, let's say. And we've got some number of distances that we observe to fast food restaurants between each of these schools, right? So the first fast food restaurant is 0.05, let's say, miles away from the first school. And then there are 4 total fast food restaurants within some buffer, let's say a mile, and so on and so forth. And unbeknownst to us, some of these schools, let's say these first, I don't know, however many, belong to this intensity function, and a second grouping of schools belong to this second intensity function. So we're going to use one layer of the nested Dirichlet process hierarchy to estimate these functions, and then we're going to use the second layer, excuse me, to do the same thing that the Dirichlet process did in estimating those subdensities. And that's where we see that these subdensities we estimated here, G sub 1, are actually themselves composed of even simpler, smaller densities. And it's also important to note here that there could be a different number, right? We're being totally agnostic about the number of components that might be required. Here, there's only 2 components required. Here, there are 3 in order to sufficiently estimate that. So we're being very agnostic about the shape of the distributions. We're also being agnostic about the kind of, the number of components we'll need and the number of clusters that may be eventually estimated. So we're being very flexible here about what we may eventually find in the data. Now here's where you have to bring in something a little bit more interesting, I suppose, because the NDP can only help us to identify the differing patterns in spatial exposure. They can't tell us which patterns are more protective of health or more deleterious to health. So we need something else. We need a different strategy to link those patterns to a health outcome of interest. Now, because we have all that flexibility I mentioned from the nested Dirichlet process, we don't get a nice, simple, straightforward answer in our estimates of, oh, this school belongs to cluster 1, oh, this school belongs to cluster 2, and so on. We get an estimate of, okay, we have some probability belief that this school belongs to cluster 1, and we have some probability belief that this school belongs to cluster 2. So we have to kind of find a way to accommodate that uncertainty in cluster assignment into a health outcome model. And I have, like I said, I can't really devote the amount of time that these methods really warrant for a full discussion, but I'm going to give some brief description of these on the next slide. And again, if you have more questions, I can refer you to an appropriate reference. But briefly, we're going to refer to these as a conservative GLM. So this is a standard generalized linear model. If you guys have ever run logistic regression, I'm basically referring to logistic regression, but we're going to, here, we'll look at the bottom first here, that conservative GLM. It's going to be a logistic regression where we only keep those schools that are consistently classified to a cluster. So we're going to lose some sample size here because there are going to be some schools that aren't consistently clustered. And that's a downside of this, of using this approach. On the other side, we could use something called a Bayesian kernel machine regression. This is going to be a little bit of a fancier model, but on the other hand, we're not going to throw any of our data away, and we're going to accommodate all the uncertainty or all the entire estimate of what probability each school has of belonging to a cluster with, say, another school. And that's what's being referred to here through this H sub j P. P, this bold P here is a pairwise probability matrix of co-cluster membership derived from the cluster assignment labels. This is used as part of the covariance of this Gaussian process. Again, if you haven't seen Gaussian processes before, don't freak out. The basic idea is that schools that have similar probabilities of being clustered together are going to have similar H's. And so if those clusters or that probability assignment has some meaningful effect or something meaningful to say about a child's proclivity to become obese, say, at a school due to fast food restaurant exposure, we'll see that reflected in the H's. All right. So I'm hoping you've got a sense of what we're going to do here. That's all. Everything thus far has been talking about what are the methods, what is kind of the high level math that's at work here. Now we're going to apply it. We're going to apply it to, we're going to use 782 high schools in California during academic year 2010 that we got through the California Department of Education. And we have about 4,000 fast food restaurants around all of those schools within 1 mile that come from basically like a digital phone book, Yellow Pages. It's called the National Establishment Time Series. We're going to use this data set in our estimation of those spatial profiles using the Nested Dirichlet process. We're then going to fit those logistic regression models I briefly described on the previous slide to estimate the proportion of obese 9th graders, including the exposure profiles as well as the other kinds of relevant covariates like something like the school's SES status, the median income of adults within the same census tract as the school, the number of students at that school in free or reduced price meals, things of that nature that we think might also explain obesity, right? We're trying to isolate the effect of fast food restaurant exposure. We're going to fit this first spatial profile identification using the Bender package that I've written. It's an R package. And I've got an introduction here. I'm hoping you guys can see. Let me just briefly switch my screen share here. Can you guys see this? Can I get a brief nod that you guys are seeing the?
Yeah.
Yep, great. So this is a quick introduction. If you want to go back to this later, I'll put a link to the slides, and I think there's a link to my website in the blurb for today. You can walk through this, and this will give you an even better, step-by-step with code kind of understanding of what's going on here in terms of the Nested Dirichlet process. What are some functions you can do to estimate everything that's going on? We've got some math. So again, I'll leave that site there. But returning now back to the slides. Let's first take a look and see if there's anything like those kind of hypothetical schools I mentioned in the first, at the very beginning. We can see that there are schools like School 1 and School 2 that maybe have a similar number of fast food restaurants. These both have about 10 fast food restaurants. But as you can see, School 1 has a lot more fast food restaurants closer to the school than School 2. You can also imagine maybe you would just use the distance to the closest fast food restaurant as kind of an ad hoc measure. But again, you might miss spatial proximity to other fast food restaurants like we see between School 3 and School 4. They both have a similar number or a similar distance to that first fast food restaurant, but School 4 has a lot more fast food restaurants close by to that first restaurant as opposed to School 3. And all of this is amidst a highly variable distance distribution. Everything you're seeing here are the school distribution of fast food restaurant distances. And you can see that amongst these schools I've highlighted, they show up all over the place. And the idea here is that there's a lot of variability, and we're hoping to capture some of that and reduce the dimensionality in estimating some of these spatial profiles in our clustering. So that's great. That shows that we're kind of on the right track in this analysis. Let's start looking at the results. The first plot I'm showing you here is that pairwise probability matrix that I mentioned on the Bayesian kernel machine regression slide. What you're seeing here at a given intersection between School 1 here and School 2 is the probability that that school is co-clustered, that School 1 is co-clustered with School 2. So the darker the cell, the higher the probability that they're co-clustered, and the lighter the cell, the less the probability. And so you can see along this diagonal, right, the diagonal is 1 because we're going to say every school has a probability of 1 to being clustered with itself. But you can see that there are about 6 clusters in spatial profiles that we identify. So 1, 2, 3, 4, 5, 6. You can also see that there are a fair amount of schools for which we don't have a lot of certainty in which cluster they belong to, right? So we don't have a lot of, a tremendous amount of certainty about which cluster these schools belong to, which cluster these schools belong to. And so again, this is kind of good because if you were to just use a point estimate to try and estimate these clusters, you would miss out on this bigger picture of how things can be a little bit fuzzy in terms of estimating these spatial profiles. Okay, if we wanted to see what those spatial profiles actually look like, we could take the median estimate and plot it. And what you would get would be something like this. You would get those six clusters I mentioned previously, again, distributed across 1 mile. And you can see a lot of variability and a lot of, what I want to say, weird shapes going on. They're almost all unimodal, but again, some of them are not. Cluster 1 here looks a little bit bimodal. Cluster 5 here looks a little weird. And so that's reinforcing our need for that non-parametric estimation. And what else do I want to say about this slide? I think the only other thing would be to say this labeling here is important for the next slide. You're going to see 1, 2, 3, 4, 5, 6. That ordering is in terms of how close the peak of that intensity function is, describing how close the fast food restaurants are to the school. As we look at these health outcome results, we want to see that what you might think intuitively is, hey, the further away the fast food restaurants are, maybe the less the probability of obesity. And so what that would mean is that as we look down these clusters, right here, these are clustered, numbered the same as the previous slide, we can see that the probability of obesity, whether represented through these blobs of H-intercepts that I've colored according to the cluster mode, or through the GLM results, which are here in brown, and their credible interval, we would want to see both of these estimates go down. I should mention that the black dot is that cluster median H-intercept. So this black dot represents about the center of all the random H-intercepts within cluster 1. This black dot represents the median for cluster 2, and so on. And so this is great because we do kind of see what we expected. It's not a huge dramatic difference, but you can see that there's about a 25% probability of obesity at schools belonging to cluster 1. And as we go further down, we can see that schools assigned to cluster 6 have about a probability of around 22% of being obese. So about a difference of 3% or so from the biggest difference to the smallest. And what's reassuring about seeing these same differences reflected in the conservative GLM is that kind of suggests that we're really capturing something real here, that the pattern is consistent, even though it is a little bit more dramatic in the conservative GLM compared to the Bayesian kernel machine regression. Okay, so that's a lot of information. I think that's all I have. Thank you for sticking with me. If you have any questions, now's the time to ask them.
Thank you, Adam. I think we have one question so far. I see in the chat room. Do you want to?
Yeah. So we have a couple of questions, I think, in addition. I also have. So one main thing is, so in simple words, you're basically trying to fit multiple distributions on the distribution of the data and figure out which distribution fits the most, or combination of which distributions fit the most.
So you can think of it as this way. We have that global density, and we're saying, okay, in order to, where's my picture of the global density? Okay, we've got a global density, right? And this global density could be decomposed in any number of ways. We're going to find the highest probability way of decomposing it according to the structure that we're imposing on it by saying, well, there are schools that have these fast food restaurants around them, and how many densities should we decompose this overall global density into in order to maximize the probability, to maximize the probability that we observe this data. I'm hoping that helps answer that question.
Yeah, so there was one person who asked, I just would like to ask the person if that, who asked them whether it helps explain it. Juhi, would that explain the answer to your question there? Okay, I'm assuming it does, so let me go on. So the next question is the optimal number of clusters determined by the nested Dirichlet process, or is it a hyperparameter that must be learned through any other optimization method?
Yeah, so it's definitely linked to a hyperparameter. So that I didn't go into any of the mathematical notation because sometimes like Dirichlet process notation is a little bit scary. I wonder if I can, I do have it in a supplementary slide. Maybe I can just point it out real quick. Okay, so you don't have to, again, if any of this stuff is making your like eyes glaze over, then don't worry about it. But the only thing I'm trying to point your eye towards here is this alpha. So alpha is alpha prime. Alpha prime is a scalar that basically describes more or less how many clusters do you need to appropriately estimate, to appropriately fit this data. And you can estimate that parameter, and that's how you estimate the correct number of clusters. So it is a part of that process of the nested Dirichlet process. It's part of the model fitting for the prior.
Okay. I have a couple of other questions. So have you considered a measure of navigability that might be relevant? For instance, suppose if you consider a mile in terms of a bird flying, whether that would differ for neighborhoods primarily navigated on foot or in cars in those cases when you're considering miles here?
Yeah, so in this data set, we just used, Euclidean distance, so as the crow flies, and you're absolutely right, it might not be the right choice. I think we used it because, I'm forgetting if there were privacy issues surrounding the data or not, but you're absolutely right that it would be better, I think, to use something like network distance or maybe Google Maps travel time or something like that. And the only thing is, or what I would say is that this method is completely generalizable to that kind of distance construction. The only thing we're really relying on here is that the distance be positive, right? Not non-negative.
So a follow-up question on that. When you're talking of spatial distances, right?
Yeah.
So would this methodology, I'm just curious to know, be applicable to other type of distances to, like when we are looking at, for example, k-means clusters, like other types of clustering, we can apply it to like not necessarily spatial distancing, but also where you consider like feature distancing is what I would say, not only Euclidean, but you can have other forms of distances between the features and where you're trying to find the clusters and all that. So is that something that would, something similar that could be applied here, or is it specific to spatial distances?
Yeah, absolutely. No, yeah, absolutely. Basically, that's yeah, you can use, like I said, you can use travel times instead of distances. If you think that that's the relevant, again, you have to reconsider your exposure profile in those terms, right? Like it would no longer be an exposure profile across distance. It would be an exposure profile across travel times according to Google Maps, or whatever kind of Manhattan distance or whatever you want to come up with. But you can absolutely do that. Like I said, just a non-negative distance metric is what we're using here.
So naively, this also seems to be a clustering technique, correct?
Yes, this is, yeah, we're clustering, absolutely. When we, this slide is basically saying, hey, you could come up with a bunch of different ways to cluster all of these schools. And if basically we had everything white on the off diagonal and only things black on the diagonal, that would basically say, hey, we have enough data to estimate exposure profiles for all of these schools individually, right? We don't need information from the other schools in order to estimate these profiles. When we find these off diagonals becoming blacker, what that's basically saying is, hey, there's something meaningful to be gained here in terms of the similarity of exposure across schools. And that's reflected in their increased probability of being clustered together.
Okay. Couple more, and then I think we will, this one. What sort of statistical method are you using to determine whether this procedure really results in features that are predictive of health outcomes?
Yeah, so basically that would be the GLM methods that I talked about at the end. If we saw, for example, I don't think I got to this here, but this this dotted line is the probability of obesity across all schools that have fast food restaurants around them. And so if all of these lines, if all of these median intercepts were basically at this dotted line, then we would say we wouldn't be learning anything from including these cluster specific intercepts, right? We would just be having the, we could just use the global intercept. Alternatively, you could think of it in the sense if you just had, I want to like reference cell coding in a logistic regression. I don't know if that's like too term dropping a thing to do, but if you had reference cell coding and a logistic regression and you used cluster assignment labels as kind of as covariates in your logistic regression, and those differences in the clusters were estimated to be 0, that would say, hey, maybe you're not learning anything from these cluster features that you're identifying. I'm hoping that answered the question. There's a lot of different ways you can use this, but the take home is something like these health outcome models I showed are the best thing you have to really find out whether or not they're predictive of health outcomes or associated with health outcomes.
Okay, thank you. And you found a difference from best to worst of 3%. That difference seems small. Is it statistically significant?
Yeah, so this is where being a Bayesian is fun, and you can think about distributions and stuff. So just to make the case simple, you can think of that cluster 1 intercept here, that triangle up here in the orange, and the cluster intercept down here in the, I don't know, magenta or pink. So that is the distribution of the probability of obesity. And so there's probably a little bit of overlap, but it's probably less than, I think when I did this, it's less than 3% or less than 4%. So again, it depends on what alpha, if you want to think of something like an alpha level or what probability you think is really meaningful, but the probability of overlap here is less than 3%. So at that level of certainty, then it is meaningfully different or statistically different. We wouldn't say statistically significant just because this is a Bayesian analysis, and alpha levels aren't typically thought of or used in this setting, but it's more or less analogous. I'm hoping that's clear.
Okay, yeah, thank you. And do you think that the covariance capture the possibility that fast food restaurants may specifically target areas with higher rates of obesity for opening restaurants and marketing? Basically, this is for marketing purposes and all that. Do you think you can, this could be used for that purpose?
Well, so there's two things. I'm reading that question too, and it's I got a different interpretation, but I'll just say that you could use it for that purpose. This could be used for marketing. Instead of schools, you could think of apartment complexes, and instead of fast food restaurants, you could think of, I don't know, gyms or green space, any kind of built environment amenity that a developer would want to use to build around, or maybe set their prices by. It could certainly be used that way. Maybe another question that might be coming through there is whether or not I'm claiming anything causal is going on here, and whether or not the fast food restaurant builders know that these areas have maybe kids that like to eat fast food and they target those areas intentionally. That could be the case. This model wouldn't tell us that. this is just a cross-sectional analysis, so it's purely an associative effect we're identifying here, not anything we could claim to be causal under realistic, assumptions.
Okay. I think we have a few more questions coming in, but in the interest of time, we will pause right here for questionings for you. We'll have Rafi present, and then afterwards, any leftover questions we can again come back to you, Adam.
Great. Thank you for your attention, everyone.
Thank you so much. It was wonderful. So thank you for sharing all your the information with us.
Yeah, that was awesome. Thank you, Adam. Should I present my screen now?
Yes, please go ahead, Rafi.
Okay. Oh, what happened? I got a word chopped off there. Okay. Hi, everyone. I'm Rafi Kurlancic. I'm a senior solutions architect at Databricks, and I'm going to talk to you about MLFlow, which is an open source project that you can all use and kind of integrate into your existing data science work. So I have a couple slides that I think will help go over the conceptual underpinnings of MLFlow, but then I'd like to also kind of show some real examples working with the APIs and running some code. And I think the procedure is like drop questions in the chat, and we'll answer them afterward. So a little bit about myself. I had a fairly winding road to get to where I am now, working with data. And I started off actually graduating nursing school, where I promptly went into trading futures. So I'm an unlicensed nurse. I played poker in college and then wound up going into trading, which worked out for a while. But about 6 or 7 years into that, what happened is that machine learning started dominating the financial markets, and the writing was on the wall, basically, that like human traders were not really a great profession to be in anymore. So I retrained myself by taking the Johns Hopkins data science specialization on Coursera. Wound up getting a job at Virtua in Mount Laurel, which is right across the bridge from Philly. I live in Cherry Hill, and there was where I really started to actually do programmatic data analysis in R and building models, things like that, trying to predict length of stay in the hospital. And also, what was the other project? Likelihood of readmission to the hospital within 30 days. After that, I went to IBM, where I kind of discovered a new role, which was technical sales, focusing on data science and open source and big data, which was really interesting, different kind of job than like a pure data science or data analyst job. From IBM, I wound up going to Databricks because I always wanted to be I always loved Apache Spark and like the promise of analyzing big data sets. So felt like, and I kind of wanted to be part of a startup too. So going to Databricks has been great. I've been here for about 1.5 years. Just a little bit about me. I'm actually from Seattle. Really love working with plants, whether it's houseplants or outdoors. And also I do most of the cooking in my house. I love playing Switch with my kids. And yeah, that's just a little about me. And I also want to talk just briefly a little bit about Databricks. So what is Databricks? It's founded by the people who were the original founders of Apache Spark, which is probably it's definitely one of the most popular open source projects for working with big data. It's a fast growing company that kind of has it's a SaaS platform available on AWS and Azure for use cases all across the analytics space, whether that's like data engineering and streaming, all the way through to exploratory data analysis, machine learning, deep learning, and SQL analytics. So there's a lot of things that you can do on Databricks. That's why it's considered a unified data analytics platform. I won't talk too much about it. That's not really the purpose of the talk, but I did just want to mention, I learned all this stuff from Databricks, and MLFlow is another open source project. In addition to Delta Lake and Spark, MLFlow is another open source project that originated from Databricks, actually from Matei Zaharia, who was the kind of original creator of Apache Spark. So that's a little bit of the background about myself and the company that I work for. To set the stage for like the motivation for MLFlow, or the impetus for why the project was created, the bottom line is that machine learning engineering or development is a complex process. So we've all kind of probably seen slides like this before. You're probably familiar with this if you're a practitioner, but you start with raw data, and then you have your cleaning scripts, you train your models, and then you have some kind of way of deploying it. That can be anything from like, saving a CSV and emailing it to somebody, or with the output of your model, or it could be like Dockerizing it and using Kubernetes and scaling it out and all those kinds of things. But what's interesting about it is that there's like so many different ways to do all these different things. So the data sets can be in totally unstructured format all the way to SQL Server relational database format. How you prepare your data can be done in multiple languages with multiple packages. Everybody kind of has their own preference for like how they do that. And the same goes for model training. There's, I mean, Adam just went through like I haven't heard of those techniques before, and I try to stay pretty close to this space. So it's rapidly evolving. There's a myriad number of techniques, and you really have to choose the right package or the right technique for your problem. And then lastly, even on the deployment front, there's a ton of options there too. So the other piece here is that this is a very iterative process. So like, not only is the whole entire cycle iterative, but even in data prep, when you're doing feature engineering, you will likely experiment with many different subsets of your data and train many different models on that. So you're tuning both on the features, and you're doing some tuning obviously with the parameters of your model and your model selection. And then there's kind of also the problem of like, once you get to big data, like how do you actually scale this out? That's another consideration. Finally, there's always the question, well, there's two more pieces here. The other big piece is reproducibility and governance, like knowing, depending upon the industry that you're in, those things can have tremendous weight. So obviously in academic research, the results really need to be repeatable. You need to be able to go back and see what was the data set that you trained the model on, and can we make these results reproducible. In industries like finance and in healthcare, there's also a lot of governance associated with, well, what kind of data did you use to train this model? Companies can get fined huge sums of money for training on data that would basically be biased against certain populations. So those are important considerations, having reproducibility and tracking of where the model came from. And then the last thing is you kind of want for data scientists to hand over models to deployment engineers or to folks who would be responsible for implementing it in applications. That's like another piece of the life cycle. So this is kind of like more than what I learned in the Johns Hopkins Coursera class, which was fantastic. But that was really focused on understanding and being able to work through this like inner circle. In the real world, there's all this other stuff that kind of goes on as well. And MLFlow is designed to kind of like manage this, help manage the explosion of data, these different frameworks, the governance piece, and being able to hand off models to other engineering teams. And the way that it does that is through a couple different components. There's essentially 4 pillars to MLFlow. The first one is, I'm going to go a little bit out of order here. The first one I would say is tracking. These are APIs that let you they wrap around your existing data science workflow, and they let you record and sort of like log metrics, parameters, arbitrary artifacts in the models themselves. Then the model objects that you're logging, they are packaged up essentially in a way that turn them into functions with their dependencies, which I'll show you this. And once you have these models, you actually have the concept of a model registry, which is like a centralized hub for where you would have visibility into what models are running in production, which ones are candidates for challenging the ones in production if you wanted to do A/B testing, and kind of have a way to manage all of that. That's what the model registry is for. And lastly, projects is the idea that, you know, if you wanted to have a to avail yourself of these benefits while still conforming to a Git type, like a Git repo or a Git repo type paradigm for organizing your code and the model objects and any other sort of like accompanying data, like the whole project as itself, there is a way to do that with MLFlow as well. I'm not really going to be touching on this one because I don't think that it's the most popular feature in MLFlow, and I don't think it's where most people get started. So in the limited time that we have, I'm going to focus more on these three. I don't think, okay, so yeah, I didn't need to build those all. So at a high level, the way that this works is you kind of like choose, you know, these are the existing libraries that you would use to train models. And then using the tracking APIs, you can log these models as MLFlow model flavors. So you would have like a TensorFlow flavor or a scikit-learn flavor or a Spark flavor or something like that. And then you can promote them from the tracking server to the model registry, where then they can be, and this is where your handoff between like data scientists and deployment engineers starts to take place. And this is where you can access them for scoring data either in batch or loading them into a stream with like Spark structured streaming. Or MLFlow has there's two other capabilities. There's the ability to turn a model into a REST API or make it accessible via REST API. So standing up a server where you can post new data to the model and get the score back. Then the last option is that there's functions actually within MLFlow to build Docker images that contain the model artifact that you've trained and all of its dependencies. So then you can take that and run it on whatever Docker or container service that your company is using. Okay, so that's the intro. Now let's actually look at some code. Scoot up here a bit. All right, so there's APIs. Let me make this bigger, and I'm actually going to pause for a second and let me know if this is readable to everyone. I think this should be good, but let me know if this is readable to everyone. Visible? Good? Okay, thanks, Adam. So this is a Databricks notebook. I'm not going to focus on the Databricks product really. This is more about, just think of, it's very similar to Jupyter. Again, the point is not to go so much into Databricks features. It's more to be like MLFlow and open source. So this is going to focus on the R API, but there's a little bit of Python in here. And like I said, there's APIs for Python, R, Java, and there's a CLI. So you have a lot of different options for how you can work with MLFlow. So in this case, we're going to install MLFlow from CRAN. And it's actually built in Python. So we have to run this install MLFlow command to essentially find the Python binaries and make sure that R is aware of where those are. You'll see that it's using Reticulate, which is an R package to communicate between R and Python. So it's a two-step process to install. You install from CRAN, and then you run install MLFlow, and then you're good to go. Now, the first concept in tracking, in MLFlow tracking, is that you're going to organize your iterations, right? All those iterations that we talked about with the whole like machine learning lifecycle, you're going to organize them into experiments. So experiments are going to be this like top level concept where each iteration is going to be logged into an experiment. The first thing I'm going to do is set the experiment to be a path in my Databricks workspace. This could equally be a path on your local machine. Okay, so this this looks basically like the same path as it would on my Mac. Okay, And we will take a look in just a few moments at what is going on in this experiment and what this looks like if you actually go into the tracking server. But before we get there, let's actually use the tracking APIs and start logging some data. So this data set we're working with is estimating wine quality. And the idea is that all of these numeric features are essentially going to tell us what the quality of the wine is. Okay, so we'll train a model to just give us a prediction on what kind of quality wine we'll have based on these numeric features. Now, the next thing is, in this case, we're going to define like a broader function for model training. We don't necessarily have to do this. We could just run the MLFlow code outside of a function. This is just a nice it's just a nice way to organize the code, I think. So this train wine quality function, it takes 3 parameters. It'll take the data set that we're going to use, and then alpha and lambda as the hyperparameters for the model. And then everything from here until here is just really kind of boilerplate, in my opinion, data science code. You split your data into training and test sets. You specify what the features are going to be and what the label is going to be. And then you're ready to start training. And the first place where MLFlow comes into the picture is this MLFlow param function. And this is really calling out to the tracking server and saying, hey, I have this parameter called alpha. This is the variable in my code that it represents it, and this is its type. Okay, so we're going to do that in for both alpha and lambda. Now, with each run, with each time I run this function, with each iteration in my experiment, we're going to continue along with our data science workflow. We will train a model, we'll do some cross-validation, and then this is, in the R API, this is a critical step to log the model. We actually use the create function from the carrier package to to turn the predict function of our model into a more generalized function with all of the dependencies associated with it. So this is kind of extracting the model object and just turning it into a function that can be ported to other processes. This is a key step in the R API of how you can hand off this model to other processes. It's more complicated in the R API than the Python one, but there's a similar function in the Python API. Okay, so after we have the model created up, we make our predictions, and then we calculate our metrics, right? Root mean squared error, and so on, R squared. And the next API that we're going to use from MLFlow is to actually log those parameters. So we'll log the alpha, we will log the lambda, log the other metrics that we calculated, and then I think things get really interesting where we're actually going to log an arbitrary artifact here. We're gonna log a plot of the cross-validation in this training run. We'll use MLFlow log artifact. Here I'm just dumping that plot to disk, and then I'm logging that directly with MLFlow log artifact. And then finally, I'll actually log the model object itself. So let me run this to define the function. Now there's 4 things we did, right? We did the parameters, the metrics, the artifact, the plot, and the model itself. So now in our training, we can call this function, pass the same data, and train with different parameters, right? Different hyperparameters. And this will kind of let us explore and tune the model accordingly. Obviously, we could define this with a different model. We use GLMNet, but we could choose random forest, or we could choose some other model that we want to use. Okay, so we're getting some messages printed to the console here, and it's telling us that we've logged these artifacts to this path on Databricks. Okay, great, looks good. Now let's actually go take a look at the tracking server and find out where all this information went. Okay, so let me come over here to all right, so this is like MLFlow hosted on Databricks, but when you install this locally or if you install this on one of your systems, it basically stands up a lightweight SQL instance. I think it's MySQL, and you know, installs the tracking server, and which has the SQL backend, and then you know, tracks all this information there. It will use another place on your local drive to store the artifacts like the plots and things like that. So this is the tracking server. This is where all the artifacts are stored. I have a unique experiment ID that I can use with other parts of the API to get this data and work with it and start exploring it with it. But I think the value of this should already be like apparent, that the ability to track all of this while you're working, you no longer have to kind of keep this information in spreadsheets or anything like that. This is all accessible, you know, programmatically and kind of like managing the machine learning lifecycle, right? If I dig into a particular run here, right? So if I click on the timestamp, this will tell me all that information we logged. It'll actually bring me back to the source for this run, this particular run. Each run has a unique run ID. And if I come down to the artifacts, we'll find, you know, some pretty awesome stuff down here. This is the arbitrary artifact that we logged. So you can, I mean, you could do some really cool stuff with this. You could log, there's packages that like Pandas Profiler where you know, basically like spits out a whole HTML document of all of the distribution and sort of like statistics of your data set that you're working with. You could log that here with every single time you train a model on that data set. So yeah, like full HTML pages or all that kind of stuff. It's pretty cool. And then obviously, probably the more important artifact is the model itself. So here is this particular model, this particular GLMNet model that we trained. And these are the, this create file will have the dependencies and stuff for this R model. Okay, so that's the tracking server, the basics of the tracking server. Let's see, how much time do I have? How much time do I have? Like 15 minutes or so?
Yeah, like 10, 15 minutes.
10, 15, okay.
Yeah, you started at 6:55.
Oh, okay. All right. So let's come back to the notebook. Let's take a look at a few other interesting things that we can do here. So all right, so let's say we want to load, you know, the best model back into memory. You can do this very simply using the path to the model artifact that I just showed you in the tracking server. So with MLFlow load model, you essentially point to the path of that model, which is, if you know, on Databricks, it's going to be this directory and then the run ID, the unique run ID. You can extract the run ID programmatically. So it's not like you have to go fishing around in the tracking server for this run ID, but that's essentially how you fetch the model object, load it back into memory, and then you can, you know, generate new predictions that way. There's two other things that I wanted to highlight just because they're, I just think they're super cool. So let me talk about the model registry real quick. I will share this notebook afterwards so you can see how to stand it up with the REST API and stuff like that. So now let's take a step back and let's imagine that we're all working on a problem together, or we all work at the same company and we have different projects. So, we have different use cases that we're working on. And I have this GLMNet model to estimate wine quality. Maybe someone else is building a model to try and like forecast wine sales or something like that. We might have different experiments, named accordingly. And without the concept of a model registry, there's no real like visibility into like the actual models that are running in production or can be considered for production and at the organization or in the machine learning practice, right? So what the registry lets you do is it lets you promote a model from a isolated experiment to a common repository. There's no APIs for this in R today, but to use it in Python is very, very straightforward. Same idea. You grab the model URI, which is the path. You could either put the path like your local path, or you could use this syntax with the runs and just point to the run ID. And then you use MLFlow register model, the path to that model, and then the name of the model that you want to, the name of this model type. You might want to name it after the use case or whatever it is. And then if you have additional versions, you simply, using very much the same kind of information, just with a slightly different function, create model version, you can push a new model to that same that same model in the central repo. You'll get a new version of that model. And there's also APIs to transition the model from staging to production and to decommission it and things like that. So if we look, or I'll show you the model registry, the UI in just a moment, but let's say you need to access these models in the model registry and score data with them. You can, similarly, you can use MLFlow load model, but this time there's a very nice feature in my opinion where essentially the URI is human readable, and this will stay stable. So this is your production wine quality estimator model. If we change the version, or if we decommission version 1 as the production one, and instead promote version 2 as the production one, this code never has to change. This will always point at what's marked as production. So you're sort of like, you can update your models without having to update your sort of production code, which is a very nice feature. Decouples that. This is what the UI looks like for the model registry in obviously this is hosted on Databricks, but same thing in open source. I gotta move this. Okay, so we're up to version 4 here. Version 2 is in production. Now, if I can, there's a little bit more here. In the interest of time, I'm just going to speak to it. There's a little bit more here where you can essentially request that a model be moved to. Let's see if I can. Okay, here. So I can request that this be decommissioned or that it goes back to staging, things like that. And again, this helps manage the life cycle of the machine learning engineering practice. So a note on the governance front, you see you have the source run here. So here I have this model that's like been promoted all the way through to this central repo. And nevertheless, I can go from this version back to the original run and back to the original code and the version of the code that was used to generate it. So there's a tremendous value there of, and MLFlow was built sort of with the tracking APIs first, and the model registry came later. So it was like a very elegant solution, in my opinion, to go from building this like foundation of being able to track and see where things came from to then having a central repo, and then you can always go back. So just as an anecdote, I was talking to a data scientist from, I think it was not overstock.com, but a similar website. I forget what the exact company was. but they were saying how they have a model registry, but they don't have any way to tie it back like elegantly to where the model came from. So he showed me on his laptop that he's like, hey, this guy put this model in here and maybe it's good, but I have no idea where this came from, so I can't use it. So this is like a really nice way to shore up that concern. All right, I'm going to talk about one other cool use case. This token is not working, but there's a really cool thing that you can do with both R and Python and Spark in MLFlow. And the idea is that, let's say you essentially use Spark to parallelize the training of your model. And you can train like 100 models, 500 models, 1,000 models in parallel. Each model will get its own set of parameters, right? Like we saw before. In the previous notebook, we did it manually where I typed in like 3 different sets of parameters. We can use Spark, and we can take a Spark data frame and have the Spark data frame have each row in the Spark data frame will be a set of parameters for training. And then we can apply a user-defined function that will take each row, run our MLFlow, our training code with the MLFlow APIs, and log that to the tracking server. So you can explore like massive spaces of parameters much faster. And it is like a grid search kind of like brute force approach. I haven't worked on using more Bayesian type approaches to with this particular pattern, but I just want to show some of the stuff that you get with that. Let me go to the experiment here. So oh, it's not going to be in this experiment. All right, in the interest of time, I won't hunt around for it. But yeah, the idea is that like in 5 minutes you could have trained. I mean, really not exaggerating. Like 3 to 5 minutes, I've trained, I don't know, like 500 models or something like that, with each having separate alphas and lambdas. And then coming back afterward and being able to search in here and figure out what the best model was. So let me come back here and wrap up. Oh, that's pretty much it, actually. Yeah. So to summarize, I guess, let's come back here. Let's see, what's a good one? That's a good one. Nah, I'm just going to talk outside. So just to summarize, right? MLFlow is an open source project that has designed to help manage the machine learning lifecycle. It has APIs that kind of wrap around your existing code to help you track models, metrics, parameters, and arbitrary artifacts that are stored in a tracking server that you can search and yeah, that you basically help you stay organized on that front. And then once you have the model that you actually want, you can deploy that in a number of different ways, also using those simple APIs, and promote them to a central kind of model registry where you can manage what's actually running in production, do all that with an eye towards governance and reproducibility and things like that. So that's what I wanted to cover. I hope I at least made that fairly clear. And then we can take questions.
Great. Thank you, Rafi. That definitely seemed, as somebody who's hasn't really messed around with machine learning before, this seems pretty approachable, and everything just kind of, it seemed clear. Everything seemed like pretty clear cut and organized. So I'm interested in looking into this.
Awesome.
We have about, I would say about 4 questions so far, but if anybody has more, add them to the chat, or, once we get through the questions in the chat, we can all just talk.
Okay.
So the first question is, this was around the start of your demo. Somebody was asking for clarification, similarities and differences with respect to tools like QBflow or CubeFlow.
CubeFlow. I don't know so much. I haven't done any like real digging into what Kubeflow is. So yeah, honestly, I wouldn't be the best person to ask. I would have to look into that. My initial thought is that that has more to do with managing deployments of containers with Kubernetes, but this is more. I feel like this can. You can use MLFlow with any like ML framework, and then for training and tracking, and then ultimately deploy models with Docker container. Yeah, Docker images and containers of the model that host the model. Great. Hopefully that helps a little bit.
A question I had added to the chat myself was when you were in the middle of giving the demo, you had gone over the log and the plot. Was that in the part where you're going through each run? So does that mean that the plot and the log get overwritten each time, or was that after all the runs have been done, it produces kind of like an end result file for each?
Yeah, that is a great question. Every single run has gets its own path and its own directory. And so the artifacts get logged to that particular run. And I mean, I've seen there's some really cool use cases for this. Like aside from logging like HTML and visualizations and things like that, if your data set's not that big, you can log the data set. Yeah, so you can really make it reproducible that way. Sometimes that's not always possible, but
cool. Yeah. So this question was asked kind of towards the end of the demo. Is there a way to set threshold on accuracy matrix here and retrain the model when we see accuracy going down below a certain threshold?
So I understand what you're asking. Let me just think for a second. So that is not built in today into MLFlow, like the monitoring of a model in production. However, it would be the fact that you have the model registry and you have that URI that's like it's like one line to load your production model back into memory. You could pretty simply, use fresh test data and evaluate the model against that, and then using the MLFlow APIs, yeah, you could script this yourself. It's not built into the project yet. Like it's not built into the MLFlow project yet. But continuing along my line of thinking there, write a script that loads the production model into memory, score it against the test set, evaluate the accuracy. If the accuracy doesn't meet your threshold, then use the model registry APIs to maybe you want to retrain the model right away, or use the model registry APIs to get that one out of there and put a different one in there. Yeah, that would be a job that you would then schedule to run on whatever basis, on whatever regular basis your use case demands. So it might be quarterly, it might be daily, it might be hourly, but yeah, I would say that the APIs are there to do that and automate that, but it's not like it's not part of the UI, not built in.
Right. And there's one more question. Are there any teams that are currently using it? What kind of cool uses have surprised you?
Oh, yes, actually, yeah, there are. Let me use a Philly one. Comcast is using it. Comcast is a very, very large Databricks customer, and they use it with their the voice recognition for the remotes. I don't have Comcast, but I know that they have a pretty big AI team over there. and they use MLFlow as like a core part of their stack. I'm actually, let me find the link and I'll put it in the, just give me a minute here. So yes, there are, and there are other customers too, but that I think is a great example. Just one moment. Here we go. There was a keynote last year. So yeah, I'll put this in the chat. There's a link to a YouTube video there. And actually on that note, our big conference is next week, Spark Summit, Spark and AI Summit. And it's totally free this year because it's virtual. And there's like topics on like the whole range of the data space. And it's not all Databricks product specific. So yeah, I mean, this link I dropped will take you to a page where Spark Summit is at the banner at the top, and there's a button to register. So definitely check it out. It's totally free, and there's stuff on machine learning and deep learning and data engineering, and like administrative stuff and the whole gamut. So I wanted to mention it. I forgot to put a slide in here, but
yeah, we can post a link to the Spark Summit registration on the meetup group in case other people are interested, especially because it's a free conference. I think that's really cool during virtual times right now.
Yep. The training is not free, but like all the breakout sessions and the keynotes and stuff, that's all free.
Awesome.
Yeah.
Great. Well, thank you so much. We're gonna stop the recording now.
Okay.